Hello everyone, today I'm going to present about my research VGAR system, Advancing Intelligent Surveillance for Real-Time Violence and Theft Detection. My name is Phạm Hoi, and I'm the main presenter of this research today. Firstly, there are some points that I will discuss in my presentation. The first is introduction, second is dataset, and the YOLO version 11 architecture, slow fast networks, and adaptive fusion mechanism between slow fast and YOLO. The sixth part is system architecture and results, and the final one is conclusion about our research. Firstly, we need to know about the background of this view, why we are developing a system about intelligent detection for theft and shoplifting. There are reward challenges. The traditional surveillance system rely on manual monitoring. Like we need to then we need to be a human or security man who stay all day just to look at the camera and um, take an action if there's something abnormal happen. But we know that not all of our human can stay all day just to look at the monitor or something. There will be times that we are tired and cannot take actions to prevent the shoplift or violent behaviors in time. So that will because the loss in a lot of retail store and there are some intelligent system that you utilize AI to do this project before, but the systems usually has high false positive rates. Like they are usually the mis the mis misunderstood of the real scenarios, and they will understand that there is not a shoplift. Why there is a real shoplift that is happening? That is might be because the lackage of data for training real effective models in those abnormal behaviors detection. And moreover, some system have high delay response times because you know that AI model need high computational resources, but in some retail stores there might be not enough space or computational requirements that is needed for those AI models, and that will also lead to the inability to process large video volumes in complex urban environments. Because in retail stores there is a lot of scenarios, like in each store there will be a different background. So how to train and how to process all of these scenarios is a quite challenge to developing system in this field. And so there is a critical need in automated real-time anomaly detection system. And finally, the market impact of the theft or the violence or the shoplift is reported to be about $100 billion annually worldwide. The next, I will introduce about VGAR, our system. Basically, what is VGAR? VGAR is an intelligent real-time system surveillance for anomaly detection. The capabilities of the system is there are some main points. There will be an object detection system with YOLO version 11, and action recognition with slow fast networks that will distinguish the action into normal or shoplift or theft or violence uh, or robbery of vandalism. And the real-time monitoring dashboard. The detected behaviors, as I have listed before, will be fighting, robbery, shoplifting, vandalism, and or just normal activity like walking or looking at the goods or the products. And finally, we develop an interactive dashboard that on the solution incorporates into 5 days of data storage and the back end for processing and the front end a React.js based front end dashboard for real-time visualization and the result of the prediction. The main contributions of our project as an hybrid architecture, a novel fusion of YOLO version 11 and Slowfast. Not only one of them work dependently, but both of them incorporate into one final system pipeline and a specific data pipeline that we where we have experimented a lot of data augmentation method for a real effective methods and data set for developing the models and algorithms in action recognitions. Finally, nextly, there will be an intelligent SLR system that will only trigger the alert with some conditions, and that leads to the 40% reduction in false positives. And finally, production-ready framework is as I have introduced before, the front and back end will be packaged into one final product, and that will be ready for real retail environments. Nextly, we will explore about the dataset. In our dataset, we will utilize some common dataset like UCF CRAM that contain about 1,900 videos and in a total of 128 hours and 13 anomaly types. Some other dataset that we collect on the internet like the abnormal activities and the shoplifting 2022. Finally, we have a custom dataset that is created in the AI laboratory of our university campus in Winyo, the FPT Winyo campus. We have created a dataset about abnormal behaviors with multi angles just for developing the models. But in fact, the dataset of on the dataset has a very high imbalance ratios because there must be more normal class than other class. So we have compared the data the class imbalance. Like the normal has, firstly we have about 12,000 videos of normal class, but only about 1,000 videos of fighting class. So we must use some approach for to address the imbalance problem. We have removed about 6,000 low quality normal samples with a resolution less than 480 and 80 pixel, and we have double on the class on the minority class with augmentation that result in 8 to 12% improvement in minority class F1 scores. Here are some of the augmentation techniques that we have implemented. Firstly, in the spatial augmentations, we apply common common methods like Gaussian and Meridian blur and the contrast enhancement and the random scaling and cropping. We will crop the randomly crop in the center or the in the center and the area where the main object of the video is moving around. Secondly, there will be temporal augmentations that will be utilized for the slow fast model that we will uniformly temporal subsampling. We will take only 30 or 32 frames of each videos and a change of 50% that we will horizontal flip the video, and finally the soft scaling we will cut off the we'll take cut off the videos. Finally, this is comparison of the original data set and the data set after we have applied on the augmentation method. There is a half in reduction of the number half reduction in the numbers of normal activities and double in the numbers of other class like fighting, robbery, shoplifting, and vandalism. In the methodology, firstly, we approach with a YOLO version 11 architecture. Key features that this YOLO version 11 model is lightweight, optimized for real time, and predict can detect the person with party boxes, and we use the confidence threshold of 0.5. But not we do not only we not only use this for human detection only, but utilize it for classification that we will fit into the model of the class like robbery, vandalism, shoplifting, and violence into the YOLO. So in our loss function, it will be the sum of the classification loss and the localization loss as well as the object loss. Here we use the 80 to 20 trend validation split and RM optimizer with learning rate of uh, with learning rate of 10 power minus 5, and we train for 100 epochs and you GPU optimize batch size. Next, we mainly used a method that use the slow fast network, as well as the YOLO version 11 method that we utilize only each frame independently to predict the action. The slow fast network is a method that split the videos into two streams. A slow frame rate stream that only use about 8 frames, and the the high frame rate stream that utilize about 32 frames to capture the rapid motion dynamics, and the features learned in the fast stream will be transferred into the slow stream that is very effective for learning temporal features in the video. Not also we use those methods independently, but we also develop an adaptive fusion mechanism that there are 3 main stages in the methodologies. First, with initial detection, the YOLO version 11 identifies suspicious objects for the action, and then the temporal validation will analyze the 32 frame clips. Then finally, the final results will only trigger if they are more than 85% confidence for more than 2 seconds, and it will result in the 40% false positive reduction, and as well as a score of recall score of 95%. This is our system architecture that combine on the AI and into the back end and the database storage, and as well as the front end. The client side will send the TBS to our site, and it will fetch and store the data from Firebase, and will send the result in WebSocket format, and finally it will send alerts into my Twilio SMS service. This is the results tables of all of our methods, the YOLO version 11. Normally, the score might be good in the precision and the recall, but in real life scenarios, the YOLO version 11 doesn't work really properly because they just utilize the spatial features but the temporal features is also an important factor in action detection problems too. As well as slow fast combined with the YOLO version 11 on the right, you can see that it achieved the perfection score on both fighting, robbery, and vandalism, because those class has unique actions that can be really clearly seen by not only our eyes but the computers can learn the features in those class very well. And finally, the real-time performance in millisecond and FPS of our total pipeline. In the total pipeline, we achieve an FPS of around 6.1, and the inference time using CPU is about 900 milliseconds, and the GPU time is about 164 milliseconds. Finally, is conclusions about the project. We achieved a high F1 score of 0.92, and the 40% reduction in form as well as 190 millisecond latency that is suitable for real-time implementation. And we have also deployed the products in 3 months for 3 months and achieved the successful deployment. There's some still limitations of the project. The F1 score of shoplifting is still low. That is because there are some in real world there are very some hard to see cases of shoplifting, like when the people doing that action might be turn their back around, or using other things to hide the camera. That is very difficult for our AI models to predict the shoplifting activities, and the current capacity is up about 2 or 3 cameras, and we need to scale up to 10 cameras to utilize better in the real life problem. And the data set diversity also need to expand more. Like there could be more classes of abnormal actions, or there should be more videos and samples in each class. Finally, our future directions will insist on attention mechanisms, developing attention mechanism for flagrant actions, and quantization, model quantization for scalability, and collect more data from real life retail chains. And finally, and the grad of CAM integration for explainability. Thank you for listening to my presentation about our ecosystem today. I really appreciate your focus.